Bismillah ar-Rahman ar-Rahim. In this video, I'm going to talk about mathematical modeling for HIV and interaction with immune system within the CD4 cells. First, mathematical modeling have been studied by Morel in 1989 and by Perelson 89 and 90, 92, 93, and by Nowak in 89 and Nowak and May 1991, 92, and by the others. In mathematical modeling, I'm going to discuss in this video four variables. The first one here, T, and infected CD4 T cells. So the CD4 T cells represented by T and infected the CD4 T cells by the virus TI in this video, in this mathematical we're going to talk about. And the infection virus, V represented by V, and non-infectious virus represented by VI. And we have parameters. The first one, the generation, the production rate of the CD4 cell, the density S, and the death rate, the natural death of the CD4 cells alpha. So the first equation, T, the T cells, and S, the production of T cells, the rate, and the natural death at the rate of T. And we have the rate that the free virus infect the CD4 cells is K. So then the first equation we have then first the production T cells and minus the death and minus that is infected by the virus at the rate K. So this is the first equation. This one is here we have is the first equation, is the first one. Okay, now the second one, now the CD4 cells infected by the virus comes as a host, produce viruses. So now the TI cells, K was the rate that the virus is infected. Okay. So KVT, the T cell infected by the virus at the rate K, and then what we have now, really TI, this infected CD4 T cells produces viruses because it comes a host of the virus HIV. Now the rate produces virus at the rate of N beta and die at the rate delta. So here what you have minus delta TI because they at the rate delta. Now the TCD4 cells infected by the virus at the rate K and becomes infected and die at the rate delta. So this one is the second one, second technical system. And for the virus and non-infectious was given here because we said M beta now produce virus as M beta, so the virus produces the rate M beta, so CD4 produces the viruses, this comes a host, and minus gamma V. And this one really virus is cleaved by the body, by the immune system at the rate gamma, at the rate gamma. So now we have the four dynamical system for differential equation with the parameters. So you find the equilibrium point and discuss the stability of the equilibrium point. When it comes stable, the immune system is stable and unstable. How to find mathematically the equilibrium point? So we have to put this one is equal to 0, and this one is equal to 0, and this one is equal to 0, and this one is equal to 0. So now each equation is equal to 0. Okay, then if each one is equal to 0, then I have the first one S minus alpha T minus K Vt is equal to 0. Now, if V the virus is 0, assume now V is 0, this the virus is equal to 0. So then what you have from here, I have here S minus alpha T equal to 0. So the TCD4 is equal to S over alpha and S greater than 0. So the first equilibrium point is S over alpha and no infected CD4 cells and the virus 0 and the non-infectious virus 0. So now this represents the stability of the immune system, represent the seropositive and it is ahead. Now this represents here, the first one. Now if the second one, if V not equal to 0, we're going to discuss this case. But see, here if I have in this one, in case of B, this beta, just want to mention this point, if this beta, this one, in this equation is equal to 1, and if I have beta is equal to 1, that is mean this one will be here 0. So now this equation comes D the derivative of this one, the differential equation, dvi, okay, and dt is equal to, this will be 0, this one, minus, I have gamma v, gamma vi. And we say that is the virus is removed from the system at the rate gamma. Now, what to solve this one? It is probable variable. So we have now v, vi over this one, v is equal to minus gamma, okay, dt. Okay, dt. So in this case, what we are in this case really, I have vi will be equal to e to the power minus gamma t and multiplied by a constant, Now, this is the t. If t increases was to infinity, what about the vi? Will be approaches what? We approaches to 0. Okay, so in this case would be not in case if this system, if v is equal, beta is equal to, if beta is equal to 1. Now, if v not equal to 0, now the point here, if v is not equal to 0, so to find the equilibrium point, really, I solve now this differential equation, the dynamical systems, and if v not equal to 0, this represents the equilibrium point where, so this is the first one here, okay, and this one the second here, because we have four-dimensional system, so we have four-dimensional system, and here this one they represent, okay, because what we said each one is equal to 0, and we have to solve. So each one equal to 0 and to solve. So because they have four-dimensional system, so now this represents the equilibrium point, and R naught, I consider R naught is this, the R naught. I consider this the R naught. So this is the R naught. That is now this R naught represent reproduction, really basic reproduction number. What mean by this one? Basic reproduction number, R naught. Really, this R naught reflects the severity of the disease. If here R naught, if we prove R naught less than 1, if R naught less than 1, that means the pathogen, the virus will be cleared. So will be clear of R naught. And I mean, if this one, this equation, if this one less than 1, that means this one, the virus will be cleared. But if we have R naught greater than 1 in this equation, in this solving system, this equation, if greater than 1, this one equation, alpha beta gamma over km beta s, if greater than 1, this one greater than 1, that is mean it's hard to control the virus and the infection. Here we have HIV virus. These what? To AIDS. If R naught is greater than 1. Now we are going to discuss when R naught is less than 1, when you have a stability. First, we have to find the Jacobian matrix. How to find now the Jacobian matrix? See, we have differential dynamical system. To find the Jacobian matrix, we have to find the derivative, partial derivative. First, T, the partial derivative of T. Here we have, I have 0. This will be here negative alpha, because T will be 1. Here what will be minus KV. That is mean the partial derivative minus alpha KV. And look at here, the first one is minus alpha KV, the first one. This is the first one. Okay, the first, the partial derivative, T with respect to T, the first one, the partial derivative. And the second now, the partial derivative, the second one, the second, if you look at the second, what the second variable Ti, infected T cells. Now the partial derivative with respect to Ti will be 0. There's no Ti, so it will be 0. So this will be 0. See, then what you have here will be 0. It is equal to 0. Then the partial derivative, V with respect to T. What about the derivative of V? Now this one 0, this one 0. So what I have here, this is the V, so it'll be minus K, it'll be 1, and T minus KT. So then I have here the minus KT. Okay, this is minus KT. And then the partial derivative here I have. With the fourth one, VI. VI we have, there is no VI here, there's no VI here. Look at the equation, there's no VI. There's V times T, so it will be 0. So look at here, then this will be here, will be 0. And be the same for the second differential equation. For the second one, this is the second one. Now the partial derivative T with respect to T time. So with respect this one to time T, so be KV. This will be here 1. So this will be here KV. And this one 0. So it will be KV. And look at here what I have. I have KV. I have KV. So, okay. Now, the partial derivative, TI. So now partial derivative TI. See, now this one, the partial derivative. What about the partial derivative of this one? Would be negative delta, negative delta. Why? Because this one zero, negative delta. So here, what I have here, negative delta. See, I have negative delta. This one. And then the partial derivative, V. So the V here will be KT. Because this would be 1, so it would be KT. This is 0, so it would be KT. And look at here, I have here KT. I have KT. And what about then, see, the partial derivative with respect to VI in this second one? Second one, there is no VI. No VI, so be 0. There is no VI, will be 0. And the same for the partial derivative V here, okay, and the third equation and the fourth differential equation given. Okay, now, this is the equilibrium point. And here with the Jacobian method. At the Jacobian method, now, at the equilibrium point, at this equilibrium point equal to this one. Okay, I substitute and get this one, the matrix. Now, to find what? To find determinant of characteristic matrix of this one. Okay, and lambda, what the characteristics, see, lambda eigenvalue, this one, the characteristic matrix here, eigenvalue, what eigenvalue lambda, minus what? The Jacobian matrix. Now, equal to, so the equation will be, this is the equation. This is the, from the determinant. What is the eta 1, eta 2, and eta 3? I explained here. And don't forget what is the R naught. R naught, this is the R naught. It's very important. This one, the R naught. Then, so now, this one, when comes is stable, less than, R naught is less than 1 here in this equation. In this equation, eta is positive, eta is positive, okay, and 3 also positive. What about now this eta 1 times eta 2 minus eta 3? This one also should be positive. If this one also positive, this one is also positive because the first one, eta 1, eta 2, eta 3 positive. But what about the difference, eta 1 times eta 2 minus eta 3? If it is also positive, that is mean what I have R naught is less than 1. So now this one is positive here. This is positive. We explained, I calculated here the equation. So this is be positive. Really, only if R naught, if this equation is less than what is less than, is less than. So that is now, that is mean the conclusion. This is the base production number. And this number, this is equation alpha delta gamma over Kn beta as each parameter. If now this one is less than 1, the virus under control. And comes stable, the immune system is stable. And if greater than 1, the HIV leads to AIDS.